Up next, I'm going to actually present my co-host for this event. It's Lee Steinke. Lee is actually a geophysicist and business executive with a track record of delivering hundreds of millions in value through leadership of science strategy and operation. Her career spans Fortune 100 to small nonprofit organizations, and she has most recently been on the executive leadership team on a $1 billion PE-backed energy company. She shares the advisory board for the Rocky Mountain Association of Geologists and volunteers at Space Foundation on a program for the United Nations Office of Outer Space Affairs. Ms. Steinke holds a bachelor's degree for UNC Chapel Hill, a master's from Yale, and an MBA from Wharton. So without further ado, I want to present my co-host, Lee Steinke.
Thank you so much, Leo.
No problem. Thank you so much, Lee.
I'd like to take this opportunity to reorient everyone to this event and the organization that created it. And then I'll turn it over to Emily Mishler with Foundation for the Future before introducing the next speaker. Please feel free to drop your LinkedIn profiles in the chat to leverage the networking benefits of this event. Blue Marble Week is a nonpartisan conversation about near-term space infrastructure from now through 2035. This monthly event is organized and produced by the Foundation for the Future. And the Foundation for the Future is dedicated to the creation of a public-private partnership for space infrastructure development. To support this cause or to sponsor Blue Marble Week, please visit our website at f4f.space, that's the number 4. We are grateful for the support of both our corporate and individual partners. And now I'll pass it to Emily Mishler to go into a bit more detail.
Wonderful. Well, it's a pleasure to meet you all and be here today. My background is in philanthropy and creative solutions for revolutionary ideas. I've recently become affiliated with the foundation and from the nonprofit perspective, and have become a partner in building the development arm of the operation. So what does that mean? That means we're financially positioning the foundation to be able to continue this important work for years, if not generations to come. From our conversations today, it's abundantly clear that our work is disruptive, necessary, and the time is now. And that means we need your help. I've been both incredibly impressed with the comprehensive vision, expertise, dedication, agility, and momentum of the speakers today, and the vision of the Foundation for the Future, the powering force behind Blue Marble Week. I believe we can all agree that the future the foundation is building is inspiring and worth investing in. This future, in space and beyond, is being built one relationship, conversation, and connection at a time. In order to continue this momentum in building and contributing to this caliber of event, conversation, and community, we need your help. We need you, our allies, attendees, partners, advocates, and friends, to spread the word about our important work through our social media, invite like-minded and like-hearted peers to our events, and to help us connect with philanthropists and organizations who believe what we believe, that our future in space is ours for the building, and the time is now. We are so excited to announce 2 different avenues to become involved if you're interested in financially supporting our work. On the corporate level, we have the opportunity to sponsor Blue Marble Week. More information is available at the QR code below. Perfect, thanks so much, Lee. And the foundation at large on a monthly and annual basis to support our important work and forward movement. If you, your friends, or family are inspired to support us as well, we welcome your contributions to support building space infrastructure and economy as we move forward. So our ask, help us bringing space home, because the time is now and the world can't wait. If you have any questions, please don't hesitate to reach out to myself, Lila, Tim, or any of our executive team or board members. Our contact information and a link to donate is available at the QR code available on the screen and is also available through our website, f4f.space. I'm happy to stick around and field any questions, and if not, thank you so much. I'm happy to turn it back over to Lee or Leo and our MCs for our regularly scheduled programming.
Thank you so much, Emily. I'll stop presenting that QR code now. Our next speaker will speak on graphene progress and its promising future for space elevators. Adrian Nixon is a founding director of Nixon Publishing Limited and editor of the Nixon Journal, an international publication on the fast-moving world of graphene and other 2D materials. Mr. Nixon has over 20 years of experience as a scientist at an international chemical company and holds several patents for his research there. He also served in global market information management and as a management consultant with a top firm. Mr. Nixon holds an MBA from the University of Bradford in the UK and is a chartered chemist and member of the Royal Society of Chemistry. He serves on the board of the International Space Elevator Consortium. Mr. Nixon, you have the screen.
Thank you very much. And Rob and I will introduce ourselves because we're doing a bit of a double act this time. So I'll be sharing my slides and Rob's going to start and then you'll see us chip in. So let's see if I can get the presentation up and running and we'll get the slides sorted.
Yay, technology works.
Hey, brilliant. Okay, over to you, Rob.
Yes. Hi, everybody. Good afternoon. And well, thanks from me and Adrian to ISEC and Foundation for the Future for giving us this opportunity. I'll do the first sort of section. Can you flip the slide, please, Adrian? So I'll do beginning. I'll do a quick sort of 101 about graphene and 2D materials for those of you who don't know much about it. I'll probably focus on the graphene powders and things like that and give you some examples of applications for the graphene powders. And then I'll hand over to Adrian, who will talk about graphene, graphene sheets of graphene and the space elevator, graphene films, and how that will work. So if you can just flip over again, Adrian. Yeah, so my name is Rob Wheeldon. I'm a director of Nixon Publishing. I've been working with Adrian for probably about the past 5 years now on Nixon Publishing and in the graphene and 2D sort of world. I originally was a business coach with well over 20 years experience helping small businesses sort of start up and grow. And more recently, as I got involved in the graphene world, I was one of the judges on the first graphene hackathon in 2019. And last year I was a tutor on the now Nano Centre for Doctoral Training at Manchester University on the commercialisation side of basically helping PhD students commercialise their research. Adrian, do you want to add anything to who you are?
Well, the excellent introduction covered everything really, apart from the
Yes.
fact that I've just got 20 years of experience in industry. And one other thing, while we're talking about graphene in this presentation, we could open it and expand out in the Q&A perhaps to cover other 2D materials which have been alluded to already, but also carbon nanotubes as well, because we're not, just because we're presenting about graphene doesn't mean that we're against carbon nanotubes at all. So we're monitoring what happens there industrially as well. So we can pick up on that in the Q&A at the end. Back to you, Rob.
Okay, can you flip the slide? And I'll just say this is who we are. We're Nixon Publishing. We produce a monthly journal on both sort of technology and the market information around graphene and 2D materials. We're in our 5th volume now, so we've been going for 5 years nearly. Then we produce individual reports. So we've recently done the report for the Foundation for the Future. We're speaking at the NASA commercialization in space next week. And we've contributed to a report to Congress on graphene and 2D materials. So if you dig that report out, you'll find us in the reference section. Can you flip the slide, please, Adrian? This is where we're based. We're based at Manchester University in the Graphene Engineering Innovation Centre. Manchester is the home of graphene. They've got the National Graphene Institute, which is the research side of things with the Nobel Prize winners. And the Engineering Innovation Centre is the business side of it. It's about helping industry gain access to the academic research and the facilities, but it's industry-led. So if you've got good ideas around applications for graphene, you go to the Engineering Innovation Centre. GEEK is how it's referred to, and you can partner with the academics and basically try your ideas out. It's about rapid development. It's about rapid sort of prototyping. It's about failing fast, which I think somebody mentioned earlier, and helping you get that idea on the road, up and running. So next slide, please, Adrian. So graphene, what is graphene? Well, for those of you who don't know, it is carbon. It's carbon that is 1 atom thick. So it's the same as diamonds and coal and stuff like that, but they're 3D materials. Graphene is a 2D material. It's 1 atom thick. Next slide, please. So where's it come from? These two guys are the Nobel Prize winners from Manchester University, Andrei Geim and Kostya Novoselov. What's interesting about graphene, prior to 2004, this stuff was considered impossible to exist. People had talked about it and thought about it, and theoretically maybe, but it was considered impossible. And what these guys did in 2004 was isolate the world's first 2D material at the university. They've got a sort of Friday afternoon program where they just, I hesitate to say goof around, but they follow the research that they want to do rather than the funded research. And using Scotch tape and pencil lead, they isolated a 2D 1 atom thick layer of carbon. They then went on to characterize the properties of this graphene, and that's what they won the 2010 Nobel Prize for. So if you flip to the next slide, Adrian, we'll understand some of the properties that they learned from isolating and characterizing graphene. So it's 200 times stronger than steel. That's why it's probably going to be a good candidate for a space elevator tether. It's the world's best conductor of electricity. Basically, it's 1 atom thick. The electrons shoot across the top, and yeah, conducts electricity really fast. It's stable. It's non-toxic. It's flexible. It's transparent. It's very, very light. But also, another reason why it's potentially a good candidate for an elevator tether is it's got the highest melting point of any material in a vacuum. It's 100 times more tear resistant than steel. It's the world's best conductor of heat. And these amazing properties, I mean, if graphene was a superhero, you know, well, it was a person, it'd be a superhero. But we're still finding new properties. So, for example, in the last 6 or 9 months, people have discovered that it's the world's most fatigue-resistant material. So you can poke it millions and billions of times and it won't break. And it's the world's most impermeable material. So if you made pipes out of it or cartons out of it, you could keep helium in it. Helium wouldn't go through the barrier. A single layer of graphene, a sheet of graphene, is as impermeable as a kilometre of glass. So it's astonishing material. It's a proper superhero. Next, please, Adrian. So this is on the left is the National Graphene Institute. That is where the Nobel Prize winners are based. It caught the attention of lots of important people, and China's been mentioned a few times today already. In 2015, President Xi Jinping of China visited the National Graphene Institute, and since 2015, the research in China has ramped up big time, and that's only the stuff that we know about. And I'm sure there's a lot going on in China that we don't know about. And if we don't sort of really get on the case of developing graphene applications, then I really do believe China is going to, if it hasn't overtaken us already, it will do pretty soon. Next, please, Adrian. So what does graphene look like? It comes in sort of two sort of forms. On the left, we've got graphene powders. Most commercial applications at the moment are based around graphene powders, and I'll give you some examples in a short while. Graphene powders are available commercially. They're available by the ton. There are lots of companies around the world manufacturing graphene powders in a whole variety of ways. On the right, you've got a photograph of a single layer film of graphene on copper foil. If you look to the left of that picture, you can see Adrian's highlighting a sort of line. That's the boundary between the copper foil on the left and the slightly shinier film of graphene. So what you're looking at there is actually a 1 atom thick layer of graphene on a piece of copper foil, which is pretty cool if you think about it, being able to see 1 atom thick. Well, I think it's really cool, but unbiased perhaps. Okay, so what do we do with graphene? Graphene powders, can you flip to the next slide, please? If there was one thing that graphene could do tomorrow, this would be it. I just think this is truly amazing. If you put tiny amounts of graphene oxide into concrete and cement, you can increase the compressive strength by at least 25%, which means that if tomorrow everybody started using graphene enhanced concrete, and we know that concrete is probably the second largest sort of creator of carbon dioxide in the world, we could probably knock about 2% off CO2 emissions tomorrow if everybody started using graphene in their concrete. Now that is an amazing thought. People are starting to use graphene in concrete. Here's an example in Cancun. It's the Yucatan Convention Center. They've used enhanced concrete initially on a parking lot and against the sea wall, and they found it so effective they actually built the whole convention center out of graphene enhanced concrete. Interestingly, okay, it makes concrete stronger, but it also has a number of properties like the rebars inside the concrete won't rust as quickly. Hence, that's why they put it on the seawall to test it. There are some experiments or research going on in the UK with using concrete in the field, and they're finding it's more waterproof. It's just amazing. And if there's one application for graphene powders, this is it. But anyway, away from Earth. Next, Adrian. Here's another example of use of graphene powders. Northwestern University have been exploring printing 3D or using regolith to 3D print graphene enhanced regolith. And basically you can make building blocks out of it. So if, for example, you're on the moon, you've got tons of regolith. If you're on Mars, you've got your regolith. Enhance it with graphene. Use stuff like polylactic acid, polyglycolic acid, which is in compost and human urine, which you'll be there anyway if you're on the moon. You can actually make some really good building blocks. So effectively, you've got the material to build stuff on the moon, build stuff on Mars. And it's strong. It's like concrete. It increases the tensile strength. So that's just a brilliant application. Next, please, Adrian. Well, I would say this is a good one as well because I'm a Brit, but this is a rocket. It's going to launch next year. It's a private, low-cost orbital company, Orbex, and the Orbex rocket will carry 150 grams of payload into space. It is primarily built with a 3D printed engine and a carbon fiber and graphene enhanced body, which makes it lighter, improves the strength, and lightweighting is what works. It's cheaper to fire it up into space. Next, please, Adrian. So that's a British example. Here's a US example. Ford cars. The Mustang F-180 in 2019 started to use graphene enhanced components under the hood in the foams and the insulation that's under the hood. They were expecting an improvement in mechanical properties, and yeah, they got it, 20% improvement in mechanical properties. They were expecting improvement in heat endurance, and yep, they got that, 30% improvement in heat endurance in the foams and things. What they didn't expect was an improvement in noise reduction. So you get a performance enhancement in terms of noise, 17% reduction in noise, completely unexpected, but amazing. And particularly at this time, if we're using our cars more as mobile offices, since we can't go to the office, or the old office that we used to go to, things like noise reduction is actually a real benefit in your cars. Since then, they've been putting it into seat foams and a whole bunch of other stuff. And we believe that last year, over 5 million graphene enhanced automobiles were manufactured in the US. So pretty much every Ford car that comes off the production line now has graphene in it. So that's a bit of a romp through what some of the amazing properties and applications of graphene and graphene powders. But Adrian's going to tell you the really clever stuff now about graphene films. Adrian.
Thanks very much, Russell. Now, as an audience, you might be listening thinking, what's all this got to do with space elevators and space? And why have we taken you through graphene powders when the really interesting stuff is in film? The reason is that it's because there is this duality in graphene at the minute. So if you're coming to the technology from the outside, you'll just hear the same word graphene, but it could mean the powder or it could mean the graphene sheet in the film. And this whole field is moving so fast that those two are being confused. So what Rob's done there is given you, hopefully, a very good understanding of the basics and taken you through some of the applications of the powders. And that is literally a tip of the iceberg. We could have gone on 10 times longer and picked whole different things. Now I'm going to focus on this graphene sheet in the film. Now, coming back to this copper foil that you can see here, this is an actual sample, picture I took at the Geek a couple of years ago. And the company that made this covered the graphene foil with, covered the copper foil with graphene. As Rob's already told you, you can see down the left-hand side the bare copper, and then you're actually seeing a 1 atom thin film of graphene covering the rest of the foil. Just think about that. What you're looking at here, as well as just the technical achievement of just actually being able to see 1 atom thin of a material, this was considered impossible before 2004. And that's a staggering achievement that we've got industrial processes that can make this stuff already here in 2021, when at the time that Brad Edwards' report on space elevator tethers had concluded carbon nanotubes were the key thing, but the problem is nobody could make the carbon nanotubes long enough. Just 1 year later, in 2004, graphene was isolated. It's interesting just thinking about the context there. So coming back to the space elevator. Now, we're all fairly familiar with the space elevator, but it does bear just going over the basics very briefly for people who might be watching this on video later. That there are various components. The space elevator is a very big structure. We've got the surface of the Earth, and then we have an earthport, which Fitz has been describing very capably, and then we have a geostationary node and an apex anchor. And then connecting all these is a stationary piece of material that goes all the way from the surface of the Earth right out to the apex anchor. And that's 100,000 kilometers long. And that piece of material is what the climber grabs hold of and then pulls itself up and down. And you can see the scale of this. This is the biggest engineering project of mankind. But, you know, hey ho, we all like big stuff. Now, that whole project was looked at by Brad Edwards and the team after NASA arguably probably came up with the first realistic proposal for the space elevator with Jerome back in the 70s. And then at the turn of the century, NASA's Institute for Advanced Concepts looked at this technology and said, look, is it really doable, or is it science fiction? And the report that came back, which reported in 2003, basically said, yes, everything is doable with today's technology, apart from one thing, which is the material you make the tether out of. And at the time, there are candidate materials, but nothing that could be made long enough. And therefore, the project has been stalled for the past decade or so. And it's sort of been tucked away in a cupboard. Now we're coming out into the open again because materials technology has moved on. As Pete Swan said, stuff is happening now and happening really quickly. And I'll take you through what's been going on. So just coming back to look at graphene. As I said before in the introduction, we're not just focusing on graphene. We are looking at other materials, carbon nanotubes, other types of 2D material as well. But for our purposes, let's just focus on graphene for the moment in the time that we have. Graphene has a tensile strength of 130 gigapascals. It's also incredibly light, as Rob said. Just think about this, 1 square meter of the stuff would weigh 0.77 milligrams. Now, you put those two things into context. What the Nobel Prize winners did, they articulated this by saying, if you made a 1 square meter hammock out of graphene and you got 4 people holding it at the corners, you could take a 4 kilogram cat and put it on the center of the 1 atom thin hammock, and it would be strong enough to hold that cat. And yet the material itself would weigh less than one of the cat's whiskers. That's sort of giving you a rough idea about how strong and light this material is. And those two properties are exactly what we need to be for a tether candidate material. And I've been working with ISEC for the last few years, presenting with these guys. They've been sort of stress testing the science behind what we've been coming up with, and it's passing all the tests. So there's no doubt that graphene can be a candidate tether material. The question now is, can graphene be made at the industrial scales needed? And interestingly, when I first started engaging with ISEC, we didn't know that it could be produced industrially. We guessed it could be, but nobody had actually done it. Since then, a lot of work's gone on with what's called the chemical vapor deposition method. So this is how that graphene sheet film, if you like, that you saw on that piece of copper was made. So we start off with a blank piece of copper foil, or there are other metals that do this, but we'll stick with copper for the moment. And you take methane, I think you guys pronounce it methane gas, natural gas, CH4. So you have a carbon atom in the middle and then 4 hydrogen atoms attached to it. Get that very hot up to about 1,000 degrees. What happens is a series of complicated reactions, but in essence, the hydrogen pulls off and the carbon lands on the surface of the metal, where the metal acts as a catalyst, or if you like, a dating agency for the carbon atoms, and they land on the surface and then connect up. Now they connect up in the lowest energy shape that they can, which turns out to be this hexagonal chicken wire that Rob showed you, that hexagonal mesh of carbon atoms connected together that is graphene. And then when the surface of the graphene's, the copper is covered, then the reaction halts. And then that means you can peel off the graphene from the metal surface, and you're left with this 1 atom thin layer of graphene sheet. That's how it's made. They're the principles, and that's called chemical vapor deposition. You might hear the term CVD. That's how the film is made. Now, there are different types. You've already heard the term single crystal graphene being mentioned already. So just to give you an understanding of what that language actually means, on the right-hand side, single crystal graphene means this perfect repeating pattern, this hexagonal molecular pattern of graphene, perfectly repeated with no holes or gaps. What we're actually finding at the moment, the industrial process of making what's called polycrystalline graphene, there's a variety of reasons for this being made at the moment. But you can see where I've highlighted the bonds in red, and you can see there are sort of 5, 6, 8 membered rings, and then there'll be holes as well, vacancies we call them. This polycrystalline graphene is nearly as strong as single crystal graphene, but these defects do weaken it significantly. So it's good enough for a variety of processes at the minute. This is where the state of the art is on the left, but we're moving very rapidly towards industrial processes being able to make single crystal graphene already. So what do I mean by a crystal? Not what you'd expect. So when I say the word crystal, I'm using this in the term a physicist would mean a crystal. Crystal to you might conjure up an image of a diamond in your hand, or a quartz crystal, something that's very hard but very brittle and will shatter if you threw it on the floor. But in this context, crystal means a repeating atomic pattern. And it could be, in terms of graphene, it would actually be something which is flexible and stretchy, a bit like plastic film you use for food wrap. I think you guys call it saran wrap in the States. We call it cling film in the UK. So that's a good analogy. The picture here isn't graphene, by the way. This is plastic wrap, just to be crystal clear. So the thing is, only single crystal graphene can realize this tremendous strength of this advanced material. So we're not only after making one atom thin layer of graphene, we're actually trying to make one atom thin layer of graphene, which is perfect at this single crystal scale. But not only that, we need to make it at a macro scale, which means making it not only at square centimeters, meters, but also kilometers, hundreds of kilometers, thousands of kilometers, hundreds of thousands of kilometers big. And that is a single molecule. Is it even possible to do that? Well, it turns out, yes. And Rob's alluded to the Chinese, and a few other presenters already have mentioned China. Single crystal graphene was first made in China, and they called it single crystal graphene, which is why we're using the term. The way that they did it was they annealed a piece of copper foil to get all the crystal boundaries out of the metal in the first place. So you start off with a single crystal of copper. And then on top of that, they then grew domains of graphene. Now you can see here on the left-hand side of this bottom shape, on the copper, the Chinese started off by making hexagonal domains, individual seed crystals, if you like, of graphene, and then they got them to grow and grow and grow and aligned them in a way so that when they grew and butted up against one another, they seamlessly connected and stitched together to form this single crystal. Hopefully that gives you an idea about how they did it. Interestingly, around the same time, just about a year later, Oak Ridge National Laboratory did the same thing, or something very similar. But the Chinese got there first. And Peking University in Beijing have made a single crystal of graphene. This is a single molecule, which is 50 mil by 500 mil. So half a yard long, 2 inches wide, that sort of scale. And that's a single molecule. And it's worthwhile just stopping and thinking about that. These are some of the biggest molecules ever grown. So is it possible to make sheet graphene at industrial speeds? We already know now that it's possible to make single crystal graphene. And we know from that test that's been done already, but in Peking and Oak Ridge, that it's possible to make the single crystals. So we now know we can scale up and scale up and scale up. The rest is process optimization to make the bigger size of single crystal. But we've got to make it at industrial speeds. Graphene is only 17 years old. Is it even possible to think about an industrial process? And it turns out the answer is yes. There are processes going on in Europe, Asia, and America already that are targeted at making industrial scales of graphene. At the moment, the state of the art, or the state of the industry, as Fitz quite cleverly nuanced, is to make polycrystalline graphene. So if you remember that stuff I told you with the red lines in it, so it's not perfect graphene at the minute, but hey, we've only been going for 17 years. Let me show you some of the machines that can make this. So Rob actually took this photograph. And this is in the basement of the GEIC, the Graphene Engineering Innovation Centre in Manchester, that building you saw earlier where we work. And this is in what's called the CVD lab. What you're looking at there is a graphene flagship supported project. Now, the graphene flagship is a €1 billion project that's been set up in Europe to fund research into graphene. And this machine here is made by a company called Extron. They're in Germany. There are only 2 of these machines in the world, and we've seen one of them, and this is the Neutron. It's a roll-to-roll process, so it makes graphene. Can you see at the top inside this machine here, where the front cover's been opened for us? You can see the top reel of graphene, of copper foil here, and it goes down through this tube furnace, which takes the temperature up to 1,000 degrees C, carefully introduces the gases that needed, and then at the bottom it reels up underneath here with graphene coating the copper foil. And we don't know what the speed is, because that's a trade secret, but they have the manufacturers have told us that this has got the capability to make 20,000 square meters of graphene a year already. Thing is, now the company here has yet to develop a separation process to get the graphene off the copper foil, but there are lots of researchers working on that in Europe already. Over to America, General Graphene in Knoxville, Tennessee. Fitzer was saying in his presentation that we've been talking to all sorts of different companies. Well, this is one of them, and General Graphene provided these images for us. What they've developed is a horizontal roll-to-roll process, industrial process. So this they have a long machine here with a horizontal furnace here where the copper foil enters the furnace, the gases are introduced, the temperature gradients are controlled, the crystal growth is controlled, and then it's reeled up at the other end. Now, the clever thing that General Graphene have done is, as well as creating graphene on the surface of the copper foil, they've actually developed a transfer process. So they can now take the copper foil from this machine here, and they've now got a continuous process where they can then take polyethylene terephthalate, plastic film. This is plastic that your plastic bottles are made out of, water bottles and soda bottles. Flexible plastic comes down in contact with the graphene layer on the metal foil, and using a trade secret process, they've got the graphene to come off the copper onto the plastic. The copper is then recycled and reused again. Already the company have told us that they can make up to 100,000 square meters per year. It's important to say here, they're not targeting space elevated tether. They're targeting the electronics industry at the moment because they're making polycrystalline graphene. However, ISEC have met with General Graphene. We've had conversations with them already. We know that they can make single crystal graphene domains already up to 300 millimeters square. And the conversations that we've had with them so far say there is no limit to the size of the single crystal graphene domain they can make. So they can make these big molecules, they can make them fast. And if they get the resources to develop the process further for other markets. At the moment, they're focused on making graphene for electronics. But interestingly, we also talked with the lead scientist, and the guy that developed this process, he actually came from Oak Ridge National Laboratory. So this was a secret process that spun out from Oak Ridge and only came out into the open in the summer of 2020. So it's only a few months that this has actually been public knowledge. Interestingly, the head scientist who invented all this is actually a space elevator enthusiast as well. So we have somebody on our side. What's it look like? This is General Graphene's picture. So we can see here that the important thing I want you to focus on here are these 4 samples in this picture here. On this side here, this is just a polyethylene terephthalate plastic with nothing on it. Then we've got 1 atomic layer of graphene on the surface. Then we've got 5 atomic layers of graphene, and then 10 atomic layers. They've already developed the process to take graphene off from the forming substrate and then layer it up in increasing layers. And that is one of the key production steps that we're going to really have to pay attention to in making a space elevator tether. Because as you probably gathered already, the space elevator tether is not made of just a single piece of graphene, a single atomic layer. It's lots and lots and lots, tens of thousands of single atomic layers all stuck together, going vertically up into the sky in a ribbon. So that's where the process is going. So what I want you to take away from this is, in the States already, you've got industrial scale manufacture of graphene. Just 17 years ago, this was impossible. These guys are not only making it, they can also make very large single crystals of graphene. They can also transfer the graphene from the copper foil onto other substrates too. So the trajectory for this, I'm sure you can actually see it's not far off, giving us a really solid foundation for manufacturing graphene tether. But we're not there yet. That's important to know. We don't go away from this saying tether can be made tomorrow. That's not right. There's still more development work that needs to be done. Can we make it fast? Well, again, this is another secret project that came out into the open last year that we found out about. And the key thing I want you to see here is the speed highlighted in this red circle here. The Koreans have already developed a vertical roll-to-roll process, very similar to the Extron machine. You get an idea of the scale there with that man holding the copper foil. They can make graphene at 60 meters per hour, which is a meter per minute already. And this is really important because what we know from talking to some of the leading scientists in the world, one of the questions we've asked is there an actual fundamental speed limit for making graphene? Because the length of the tether is such that we're going to have incredibly fast manufacturing speeds. Meters per second is probably the area that we're going to be in, and probably a bit faster. And we needed to know, is there actually a fundamental speed limit to which you can make graphene? And it turns out the answer is no. You're not limited by the atoms coming together. There are other mechanical limitations that would come in. And what the Koreans are showing us here is they've already got the speed up to a meter per minute and making high quality graphene there. So we know that we should be able to move and optimize this process to go faster and faster and faster. Really impressive stuff. And a lot of this has been going on in secret. So we've gone from impossible to industrial in just 17 years. 2004, a year after Brad Edwards' report, second issue came out. Then before that, graphene and 2D materials were thought to be impossible. Then the Nobel Prizes awarded. That triggered a technology hype phase. People dived in, and then they suddenly found, oh gosh, we just got graphene black powders. They added them into things, it made it worse. Lots of investors lost their shirts. People, you'll probably talk to people who say graphene's overhyped. That comes from that 2010 and probably through to about 2014, 2015 phase. We're through all that now. As you've seen from Rob's presentation, we actually know how to deal with powders. They're making fantastic additions to all sorts of industrial scale stuff. 5 million Ford cars out there already. The pace with which graphene is progressing, the manufacture of the sheet graphene and single crystal graphene is moving faster than anybody ever expects. We're monitoring this on a monthly basis, probably actually a daily basis. And every single month that we produce an issue of the journal, we get surprised at the rate of development that's taken place. So what I want you to take away from this is sheet graphene, single crystal graphene, these are important terms. It's separate from the powders, and the single crystal sheet graphene is the material we're focused on for the space elevator tether. This ain't science fiction anymore, guys. This is industrial reality, and the trajectory this is on is moving so fast that we can almost guarantee that the industrial capability to make space elevator tether will happen at some point in the future. Just a question now, resource, time, effort being put in to optimize these processes. So that's us, that's our questions. Hopefully that's been of interest. I'll stop sharing the screen and I can, and we'll take you back and we'll see if we can take some questions. Was there anything else I missed, Rob?
No, I don't think so. I
reckon,
noticed
guys?
that Dennis asked a question about powders and phones in the cars. How does it reduce the noise? And it's to do with the size of the holes or bubbles in the foams.
Yeah, Dennis, it's polyurethane foams, and when there are bubbles that form in the foam as a result of the manufacturing process, and what the graphene powder seems to do, it makes lots of smaller bubbles which attenuate the sound. And as Rob said in his presentation, that came as a surprise. Nobody expected that.
Great, sounds great. This is Vern. Adrian and Rob, every time I hear your presentation, I learn something. It's fabulous what you guys are doing. I maybe learned that my new SUV has graphene in it. Who knows?
Yeah, you've got graphene in it.
It is a Ford product.
Yeah.
But I do see, serious comment, I think if we focus on the elements of the space elevator beyond the tether, the climber itself, the containers that will be released at GEO, and elements like that, you can see quite a bit of applications for graphene powders, even to make them stronger, lighter, etc. We make the climber lighter. The implication, of course, is the payload can be bigger. So it's tremendous future there.
Yeah, and Rob, you pointed out the Orbex rocket body. That was
Orbex rocket.
Yeah, that's what got me thinking. Exactly.
Yeah. And Vern, this is one of the things about working in this field. We're right at the edge of what's possible, and it's not just us that, not just you that would learn from this. We're learning all the time as well, and because graphene is a multifunctional material, as Rob showed you, world's best conductor of electricity and heat.
Oh, unbelievable!
Impermeable. You name it. You can think about applications that we haven't even dreamt up yet.
Well, the concrete example with the being electrically conductive, you could have designed a building that could monitor itself.
Yeah, and as
build the sensors into the fabric of the building, so it just tells you when it's going to fall down, I suppose.
And as Fitzer was saying as well, we're going to need testing, we're going to need sensors, we're going to need data sources and information about status that we can't even dream up yet. But actually, this material is probably capable of being created to build things in. We're already getting things like radio frequency antennas being made from graphene. And actually, graphene is now moving into the terahertz region of the spectrum. So it can actually emit terahertz, it can actually detect it. So we could find that graphene underlies the next generation of terahertz telescopes, perhaps.
Well, just thinking of the antennas that will be involved in the operations at GEO with the flying robots, the climbers themselves will have, if you can eliminate the weight and the bulk of those, and it's a tremendous application there also.
Yeah, and Michael, when we were practicing this, you showed me your jar of carbon nanotubes. It might be that the lessons we're learning from manufacturing 2D materials might translate over to manufacturing carbon nanotubes. And the moment carbon nanotubes can't be manufactured in any, the longest I've seen is 500 mil, but really when they're talking about ultra long nanotubes, they're still talking about millimeters.
Yeah.
So this could unlock processes that we don't even know about yet.
When you were showing those pictures, I took my glasses off and got in really close to look at the pictures, and then I went to General Graphene to look at their stuff. Their machine is pretty interesting compared to what we were doing. We were doing a CDV version also, but as Pete said, it's about time to throw those out, because what we created, almost 15, almost 20 years ago, it's junk. I mean, it was junk then, and it's definitely not even in the ballpark now. So I was wondering exactly what you just mentioned. Are there ways to use the new techniques and kind of reverse engineer and figure out what we were doing wrong?
And don't beat yourself up about making junk. You've got to fail a lot, as Fitzer said as well. This is tolerating failure to learn. We're standing on your shoulders and the work that's gone before.
You're standing on a lot smarter than my shoulders. Let's be really clear. Like we stopped for a very good reason. There were way more people smarter at this than we were. But thank you, I appreciate it.
Yeah. Pete, do you want to say anything, or Fitzer, do you want to say anything about General Graphene in this forum?
Well, Fitzer would be the one to say it. I don't know if he's got a connection through Michael now. But the real kicker is we have efforts across the globe to work with whomever has good technology and materials and stuff like that. And we had a meeting with General Graphene with many of our board of director members, and Adrian was there, and Rob, I'm not sure whether you were there. I think you were, but anyway, it was a good meeting. talking about where they were and where they were going. And I'll tell you what I gained from it was there was a really, really smart lady who came from Oak Ridge and joined the company. And this is an extremely important point I want to keep making to everybody. She left the research organization in the government to go into industry because she believed in the material. And she believes she can make magic material like a space elevator tether. She's there trying to figure out how it's accomplished. You don't get products like that in government research organizations. You get them in private industry where they make their money and, you know, have a good career. So the discussion with General Graphene was marvelous and really encouraged me that the tether for the space elevator will be ready before the pundits think it will be. And it's like so many other technologies, the uses out there are monumental. And when the uses start demanding the material will develop faster. One point I wanted to make, Adrian, is we at Isaac and Adrian in Manchester have been working with the British Interplanetary Society. And we wanted to have a one-day society meeting that would be this magic material with space. Now, we didn't call it that, of course, but one day would be space structures and space. I mean, the morning or the afternoon would be space structures and stuff like that. And I have an experience in the R&D arena where I asked some people building futuristic satellites, what would they do if their spacecraft weighed 1/4 of what it is today? And it's remarkable what they can do if they can, you know, have 3/4 of the mass thrown away. And so the application of these materials, as simple as holding hydrogen in a tank, can really, really make a difference. And then the battery mass, holy Toledo, the battery mass, things like that. So we wanted to have a one-day British Interplanetary Society meeting, and the morning would be the materials with spacecraft and stuff like that, and then the afternoon would be, voila, a space elevator needs a tether. And we were well along the way. We had set a date and everything else, and then the coronavirus came along. So we probably will have something in the next 9 months or a year. We've got to get into the schedule. Those guys are really busy. They have a lot going on.
Hey, Pete, just a couple days ago, one of my professors, Dr. Chris Welch, just 2 days ago became the new president of the British Interplanetary Society, and he's a big space elevator fan, going all the way back to Clark. He knew Clark. He's British. He knew Clark.
Yeah, I know him. And I've been a fellow of the BIS, and I don't get too impressed because I was a foreigner, and all I needed to do was send money and say I was in a PhD program, and they said, "Oh, you got to be a fellow." And so anyway, so I got to be a fellow, and I have really, truly enjoyed the professional relationship with the BIS because it's a remarkable organization. In fact, I mean, just a little aside, I think Isaac is set up as a model based around the British Interplanetary Society. We're like a small little parallel organization. But anyway, it's remarkable activities. So I think, you know, Adrian and Rob's presentation shows that there is great hope on the material being ready when our mega project is ready for that material. They're both going to take 10, 12 years, but we should be able to beat the 2035 goal of the Foundation for the Future. So, you know, we should be right in there with that activity.
Yeah. Fitzer, did you want to add anything about General Graphene? Because I know you've been talking with them. You're still trying to connect through. Rob, there was another question here from Inara in the side panel.
Where is it?
Is anyone working on graphene cables for use on Earth infrastructure?
Graphene cables.
So we've been talking about this quite a bit, actually. You could make bridges out of this, suspension bridges. You can make suspension bridge cables out of layered graphene. but also there's one bunch of people that have sort of brushed up against us on the in our network, and they're looking at using is it these flying windmills, Rob? Like a tethered aircraft.
Yeah.
And the propellers whiz around, but then they generate electricity. But the problem is they've got a problem because they can't get an electrically conductive cable that's light enough and strong enough to connect the ground.
Then somebody else we've been working with, one of the if you could lay if you've got your sort of data cables and things like that, if you can lay strips of or any other cables, a trail of graphene, you've got a cable that can go underground and then basically tell you when it's broken. One of the problems that people have with the cables that break underground is where is it broken? So you might have to dig up, yards and yards and yards of pavement, sidewalks or roads to find out where the cable is broken. Whereas if you put the sensor along the cable, it can tell you almost exactly where it's broken. And we've been talking with utility companies, water company in the UK, around their pipes. A lot of the pipe work in the UK is old, and so what they do is they put in a plastic sort of inner, they're old metal pipes, and they put a plastic inner in. But if that breaks, the leak can turn up a mile from where it's actually broken. So if you can build sensors into your piping, you know exactly where this sort of, where it's broken. Brilliant.
Yeah, Rob, I can understand when the pipes are 500 years old that you need a little bit of help.
Yeah.
We don't have anything 500 years old in the U.S.
Yeah, but just the idea of building these sensors into things, the idea of remote sensing in a building, is just pretty cool.
Yeah, and thankfully, my cable wasn't broken, so I'm back.
Adrian, this is Spitzer. I finally was able to get back in. It's amazing, Michael. Like I said, enough turmoil to make it memorable, and it's almost as tough as being thrown down the elevator shaft by the undersecretary. General Graphene has something that we all on this phone call should learn, is that when a reasonably well underwritten company, has put together a formula and a plan, they can make amazing products or projects or progress or all of those things. And that's what we're seeing with General Graphene. So when I introduced Tim to General Graphene 3 or 4 months ago, the first thing Tim did was said, I need to see some samples, And we turned that around in 7 or 8 weeks over Christmas holidays. The notion that we have a single molecular layer of, and I have to say, arguably, single crystal graphene being made may actually set aside the progress that the Peking University progress was all about 4 years ago. Because the samples, at least arguably, came from the CVD production line that General Graphene is putting together. Now, it was sort of handheld. It was, hand carried down the line, as it were, and whatnot. But I expect, frankly, the same kind of progress in the other engineering shortcomings that we're dealing with. And what is engineering shortcomings? Engineering shortcomings means that we need to test things and figure out the difference between success and where we're at. And General Graphene has demonstrated that to all of us here. And they have been very open with their progress. Okay, Pete, I'll surrender my phone again.
Now that you're in, make sure you stick in, because you're going to run the panel in a little while.
Okay, I'll run the panel in the blind as long as somebody can put the charts up. Yes, sir.
Yeah, we can handle that. Okay. Any more questions for Adrian and Rob? It's getting a little late back there, so we want to,
It's
pat
dark
them on the back. Yeah.
Yeah, I
Adrian,
actually had a question for Adrian and Rob here. Kind of in the previous panel that was outside of this, you guys spoke about graphene, and it's kind of amazing the amount of progress, as you said, just even from a couple months ago when you gave a similar presentation. And you were talking about how there was a limited focus in the United States on manufacturing even polycrystal graphene as opposed to the benefits of the powder, just for its utility alone. How do you foresee, building up the requisite scale, like the demand for this kind of product at the kind of scales we're talking about? Because correct me if I'm wrong, but the space elevator, we talk about it being 100,000 kilometers in length, but we don't need just 100,000 kilometer strand. We need perhaps hundreds if not thousands of layers of 100,000 kilometer single crystal graphene sheets, and like that becomes an industrial scale, which is not going to function if the space elevator is the sole customer. So what do you foresee as sort of the additional customer uses? Like we've discussed briefly, like measuring pipelines, but how do you see a greater, shall we say, thousands of kilometers scale demand that pushes this market moving forward?
Rob, do you want to start off and I'll take over?
Well, at the moment, it's still very much it's about the markets to start with. It's still very much a producer-led market. So people are making stuff and then trying to find a use for it. And so it's a push. We're pushing powders out. We're pushing, general graphene. We're pushing out, polycrystalline graphene sheets and things like that. Something has got to flip so it becomes a market pull. You're beginning to see that with the powders. So if Ford are putting it in all their cars, there's a pull. So if there's a pull from the market, somebody's going to dive in and say, right, we can meet that demand. For the powders, there are lots of new ways that people are coming up with to manufacture graphene powders. James Tour at Rice has got his flash graphene. Was it graphene CR? Used biochar to make graphene. So basically, you're making graphene out of trash, out of vegetation. But with the Fords and potentially with concrete, there's going to become a market pull. For the sheet graphenes, we're still very much in that early days where we're pushing stuff out, and trying to work out, what can we do with it? Okay, we can make sensors with it. We haven't got the quantities to make elevator cables, even for, your skyscraper. But that might be the next sort of stage.
Yeah.
I'm
sorry, I thought you were finished. We do have some additional questions in the chat for when you're finished.
Okay. And then there's getting the volume. You're only going to get the volume when there's a market pull.
So yeah, if I can just take over from Rob, I know Michael, you wanted to ask a question too. Oh, okay. So specific market pull for sheet graphene at the minute, because it can be made in small quantities. And for electronics markets, we're already seeing things like Hall sensors being made, and these are particularly they're so good. These are little sensors that detect magnetic fields, and 2D materials are brilliant at detecting these, because you can hold one of these sensors and rotate it in the magnetic field, or the magnetic field can rotate relative to it, and it doesn't get affected because it's a two-dimensional structure, whereas normal sensors, they have the third dimension, and the magnetic field warps where the electrons move in it. So these new graphene sensors are already beating the calibration equipment that's being used to test sensors. It's now being, there's a company called Cardia in California, not far from Fitzer and Verne. They're using CVD graphene to make sensors that can detect COVID. And so you've got now a lab on a chip where you get an instant electronic readout that tells you if you've got COVID, what stage you're at, have you had it, or are you about to get sick? So they're on the market pretty much already about now. As we start to scale up and get larger quantities, the stuff on mobile phones here, sorry, cell phones, when you drop this, it breaks. And the reason it breaks is because the material on the screen, you can already make flexible displays, but you can't make the touch screen bit flexible. That's something called indium tin oxide, which is transparent and electrically conductive. And if you remember back to Rob's presentation at the beginning, you might remember that graphene is transparent and electrically conductive. And although it's not cheaper than indium tin oxide, it can do something ITO can't, which is you make a mobile phone screen with graphene on it, you can roll your phone up, or you can drop it and it won't break. And flexible touch screens are a $98 billion market just by itself, Kevin. So these things are starting to kick out. In fact, where you're going, Kevin, with your question was, what markets are there now which will provide economic returns so that we can build up to make a space elevator tether? It's not that the markets don't exist, although there's some market education to do. It's one of the things as we project forward is these markets are so lucrative and so demanding that they might distract us from making a tether in the first place. And then they'll scale up and scale up and scale up. One other thing, just very quickly, you can layer graphene up, thousands of layers, and you'll make something that's as thin as saran wrap, and that would stop a bullet. And as Fitz is quite keen to point out, very lightweight and very strong materials are what are required for an awful lot of aerospace applications, defense applications, things like that. So you can imagine, that you could have bulletproof armor, which weighs next to nothing. Somebody Rob and I know he's an ex-Navy SEAL, and he knows just how valuable it is to have very, very lightweight stuff, because the special forces often drop their armor plating just for lightweight movement about. So does that sort of begin to answer your question, Kevin, about where the economic returns are and where the trajectory could be?
Can I put it in a little perspective on infrastructure? It turns out that this whole push that the Foundation for the Freedom or for the Future is going with is space infrastructure. But in America, and I'm sure it's true in the rest of the world, infrastructure is falling apart. I mean, it's about 50, 75 years after World War II. I've got to subtract here, 75. And we put in a lot of infrastructure in the 50s. And that infrastructure, bridges, buildings, everything else, is starting to wear significantly. And my vision of polycrystalline is you make sheets of that, wrap it around a cable on the Golden Gate Bridge, and you've extended that cable life by, pick a number, 50 years. And if we could get infrastructure demanding sheet graphene, we're talking about a tremendous need that would drive, it would be a demand pull, but it would be extremely important to the nation's health, all, globally. If we make sure that bridges don't fall down and infrastructure is working and the power cables are working and all that kind of stuff, which is, part of the Congress's push to have some infrastructure money invested. I think that's an area that has not been approached very much with the new materials.
I agree with you, Pete. Rob, do you want to say something briefly about, sorry, Michael, do you want to say something briefly about graphene asphalt?
Yeah, in the UK and in Italy, they've been putting graphene into asphalt. So in Italy, they've done tests on a stretch of road near Rome, and more recently at Fiumicino Airport, they've put graphene in one of the taxiways. In the UK, they've been testing it out on some of the highways, and basically, if you put graphene into asphalt, it improves the strength and temperature sort of range that you can cope with. It decreases rutting, so you don't get the sort of grooves in the roads as they get used.
It basically doubles the service life of the road.
Yeah. I mean, again, it's small quantities, and it's things like that. Yeah, once you start getting into construction, into roads, into concrete, into buildings, that's when the real market starts to grow.
All right.
We're talking about cables, elevator cables. You could build a building as tall as you ever want.
We better let Lee get
We are
halfway.
actually out of time for this segment. Perhaps we could revisit another day. There are additional questions popping up on all our different platforms, so a lot of interest in this topic. But I don't want to cut Dr. Swan short.